Hello guys, in these videos we will understand about the linear block code of ECC. In last videos we already have learned about that what is error correcting code and where it is used, what is the applications and how we can describe the error correcting code. So now in these videos the linear block code we will understand. So in this session we will cover the following topics. First we will begin with the types of error correcting code to understand how they are classified. We will discuss the linear block code, one of the widely used techniques in digital communication. So third we'll explore how linear block coding works to detect and correct errors in transmitting data. Fourth, we will go through the complete encoding process with a simple example to help you grasp the concept clearly. Fifth, we will introduce generator matrix and parity check matrix, which are essential tools in encoding and decoding process. And finally, we will wrap up with some numerical problems so we can apply this concept practically and strengthen your understanding. Okay, so let's get started. Error correcting codes are used to detect any errors that might occur during the transmission of data. So these code work by adding extra bit, which is called the redundancy bits. Okay, and which we can also say that is called parity bits. Okay, to the original bit stream. At the receiving end, these extra bits helps to identify whether an error has occurred or not in the transmitted data. So some common example of error detection codes include the parity code and the Hamming code. So basically these type of techniques we can use to identify inside the message bit it is occurred or not, that means error is occurred or not. So after then we can easily find out the position of the error and we can easily correct them, okay, using the error correction code. So error correction code are also used to correct the errors present in the received data so that we will get the original data. The error correcting codes find the correct number of corrected bit and their position in the message. So using correction code we can easily find out the position and the data. So there are two types of ECC error correcting codes, which are as follows: linear block code and convolutional codes. So linear block codes is fixed size block of bits. The message is contained. The redundant bits are added for correcting and detecting errors. The second type is convolutional code. In this method, data is sent as a continuous stream and parity bits are generated using a sliding application of Boolean function to the data stream. After some videos, we will see this topic about the convolutional code. Among these, the Hamming code technique is a popular method used for the error correction in digital communication system. So for encoding, that means whenever we want to send the data from one point to another point, with the source to destination, that time we want to use the linear block code to encoding, and after then we want to use Hamming code to decode at the receiving end. So now let's go to that slide where we can understand that what is linear block code. Linear block code is a type of error correcting code used to detect and correct errors in digital data. They are called linear because the encoding process involves linear operations. So you can see the message which is over here 0100101. After encoding, it will create a code word which is after encoding means the encrypted code it is called. So basically there have single line code like that linear code, okay, linear combinations code 1001101. So this is the linear combination original data which is encrypted after encoding. So using the linear block code we can do these things with our original data. So this works by breaking the message into fixed size block, and extra bits, that means the redundancy bits, are added to each block to help detect at the receiving end and the correct at the receiving end. So it is used when the message has defined length. So that means when the message has a specific length, we can easily convert the data from one message, that means message bit, to the encoding bit or encoded or the code word. So basically the example of this linear block code is Hamming code, Reed-Solomon code. Okay, here it is removed actually, but it will be this Reed-Solomon code. Okay, next simple example like how the error actually detecting and how this error can be correct. So let's look at how it works. So here we can see the message is 1001011. The system might send 0001011. The extra bit shown as P here, P is stands for parity bit. Okay, so P here are for checking and fixing errors. If an error occurred during transmission, like changing one bit from 0 to 1, the redundancy bit helps the system to detect and correct the errors on the receiving side. And that's how linear block codes improve the reliability and data communications. So let's go to the next slide where we can understand how linear block code will work. This process involves three main steps. First is encoding, where the original data is encoded using a generator matrix. So here one word is new for you, that generator matrix. Later we can easily understand the what is generator matrix and how we can create our own generator matrix. To encoding our message to produce a code word. Okay, so basically encrypted code word we actually want to create using this encoding process, and the linear block code is the one more encoding process. So this generator matrix to produce a code word. Second step is transmission, where this code word is sent over a communication channel where errors may occur. That is, the code word is transmitted over a channel where error may occur. And the third point is decoding, where the received code word is checked using a parity check matrix. So this is one more point which you can understand at the receiving end to detect and correct the error. That means the where the error is occurred, the position, and where the which data is occurred. So basically the data we can change and also we can correct the data. So the mathematical expression for or rule for encoding is as follows. So basically in linear block code we have a mathematical expression. So let's assume m is equal to message. Message means the message data. The message vector, or we can say the data vector. Later we can understand the message vector of length k. Okay, so it has a length, and the length we are denoting using the k word, and the m is equal to message vector, or we can say data vector of length k. Okay, G equal to capital G is equal to generator matrix of size k cross n. So k cross n you can easily identify like this, that k is the row number and n is the column number, and the c equal to code word vector of the length n. Then the encoded code word is given by that c equal to m cross g, that means m into g. So basically the m or the data vector or the message vector will be multiplied with the generator matrix, and this will be the your code word. After doing the calculation, it will be the code word. This multiplication will using module 2, and one more point over here, the multiplication is done over module 2 binary arithmetic. C or code word is transmitted over the convention channel. So one note you can see over here, the multiplication is performed using modulo 2 arithmetic. Means this ensures that the code word not only carries the original message, but also it includes additional parity bits that make it possible to detect and even correct errors during transmission. So that means with the original bits, it is adding a parity bits. So that's why the multiplication is done over mod 2. Now let's go to the next slide. So here we can see how the generator matrix we can create. So let's look at simple example of linear block coding using generator matrix. We have 3, 2. So 3, the first one, whenever we will write inside the parenthesis 3, 2 or 4, 6 or 7, 4 like this, then which means one is 3, 3 is the code word, and 2 is the data bit. Data bit means the message bit, and 1 is the redundant bit. So out of 3 bit, so total code word is 3 bit. So out of total code word we have 2 bits. One is the 2 bits, 2 bits for data bits. That means basically we can say like this, out of 3 bits, 2 is for the database and 1 is for redundant bits. Redundant bits we can say also the parity bits. So 2 plus 1 equal to 3. So 3 bit is the code word. Got it? Next, generator matrix where first two columns for data bits, and last column for parity. So first two columns, you can see the generator matrix, one matrix is written over here. So 1 0, the column wise you can see 1 0 0 1. So these two columns for data bits, and the last one columns like 1 and 1 is called parity bits. So you can think like this, but later we can understand that what have inside it, inside the generator matrix. So message or data bits, like let's assume that we want to send a message which is where the digits are included 1 0. So this is the message m equal to 1 0. So these things you want to send, this message you want to send through wireless or the through wired communication. So now the code word calculation is C equal to M cross G. Before we understand already, so the message bit will be multiplied with the generator matrix. So multiply message M with generator matrix, which will be calculated with the mod 2. So now how we can calculate? So now you need to assume this is the generator matrix, 3 cross 2, sorry, row cross column, it will be there. So that means 2 cross 3. 2 cross 3 will be there. 2 is the data bits and 3 is the code word. I know this is little complicated because sometimes you need to write down inside the brackets n comma k, and sometimes you need to write down in a row and column wise like 2 cross 3. So that's why next slide we can understand what is the meaning and what is relations in between these. So code word multiply message m with generator matrix, basically we can understand and we can easily create our matrix like the code word. So using 1 and 0, this is the message, cross 1 0 0 1 1 1, this is the generator matrix. Now how we can calculate? So first column, when a first number will be multiplied with these two column, 1 into 1 plus 1 into 0, sorry, 0 into 0. So 1 into 1 equal to 1 and plus 0 into 0 equal to 0. That means 1 plus 0 is equal to 1. So the first code in code word, the first digit will be the 1. After then 1 into 0 plus 0 into 1. So the both the time will be 0. The 0 plus 0 is equal to 0. The next code word, next digit will be 0 for the second code word. Next, second digit of the code word. Next, 1 into 1 plus 0 into 1. That means 1 will be the result, the last code word. So 1 comma 0 comma 1, this will be the your code word after conversion or the after encoding. So now for this time you can easily calculate this message bit with the generator matrix, and this message bit, when it will multiply with the generator matrix, then it will create a code word which we can send through transmitter. Transmitter means the any medium like the wired or the wireless. Okay, so that's why we this way we can create our encoding. That means this is the encoding process. So now next slide is very important. So this is our generator matrix. What is generator matrix? Generator matrix is a matrix used in linear block coding to encode the message bits into a code word. We already have seen some of the one example how the generator matrix is calculating by the message bit, and it is creating a code word which is actually sent through wired communication or the wireless communication. So by adding redundancy bits for error detection and correction, we want to see that how we can create our generator matrix to send, like generator matrix it is not created before, so it will be created at the time of sending, okay, with the message bit. So after encoding it will be sent. So that's why into identify that how we can create our own generator matrix for to send or for encoding the message bit into code word. So it has k rows. So you already have seen the last slide, 1 0 0 1 1 1. So there have 2 rows and 3 columns. So that means 2 cross 3 we can write down. So same way you can see the k equal to number of data bits, and number of bits in the code word. So number of bits in the code word means the 3. let's assume that 3 comma 2. So here let's see, the generator matrix defines how message bits are combined with parity bits to form the final code word. So now we need to understand about this portion. It has k row and n columns. Okay, n column is also equal with the number of bits in the code word. So that means 3, if 3 is written in the inside the bracket, that means first bracket. So what is written over here? 3 comma 2, 3 comma 2. So basically 3 is the code word and also 3 is the column. Next, k equal to 2. So 2 is the row and also 2 is the data bits or the message bits. We can see the data bits or the message bits has length k. That means that k is equal to message bit, k is equal to data bits, and it also defining the row in a generator matrix. So now let's clear these things step by step how we can create our generator matrix. So decide n comma k. First you have to decide that what code words you have to convert. So like 7 comma 4, like 8 comma 9, 8 comma 4, 6, like this. Okay, number of code words bits and the data bits. The matrix should have k rows and n columns. That means generator matrix should have k rows and n columns. So always row will you have to write down at the front and then column. So place an identity matrix of size k on that left side and parity columns on the right side to create redundancy. So these all steps we will see in the next video. So now here you can clear your all doubts. What is k, what is n, everything. So now in linear block code, whenever you are writing inside the bracket n comma k, that means n equal to total number of bits in the code word after encoding. But k equal to number of message bit, which is also called data vector length. So data vector denotes by m also. Okay, that is message bit, which is also equal to k, that means message bit. So k is the data vector length and m is the message bit. So in generator matrix, the length is k cross n, means n equal to number of columns, k equal to number of rows. So in generator matrix, that is inside the bracket k cross n we have to write down. So now generator matrix used for add redundancy code into linear block code. K equal to row, which is also equal to number of message bits, which is also equal to length or dimension of data vector. All are same. So same way also we can understand over here that n equal to columns, which is in generator matrix, which is also equal to number of code word in linear block code, and which is also equal to the length of the code word. If in exam there have a question that what is the length of code word, so you can write down n equal to length of code word. All are same. Okay, so now next slide we understand about the how we can create our generator matrix. So now let's say we want to create a n equal to 5, k equal to 3 linear block code, 3 data bits, 2 parity bits, total 5 bits in a code word. So you can see that n equal to 5 means there the 3 is the message bit which is added with the parity bit, and what will be the parity bit? 5 minus 3 equal to 2. So that means 2 is the parity bit. So 3 data bits and 2 is the parity bit. So now 5 bit is the in a code word. In a code word, what we have to do first? We have to create our identity matrix of 3 cross 3. That means the 3 cross 3 square matrix with the identity matrix. You need to create a identity matrix with a k equal to 4. I say k equal to 3. So here for this question, you can see the k equal to 3 means the one identity matrix it is created. Okay, so all the diagonal digits will be 1, remaining will be 0. So first step, you have to create an identity matrix with the k equal to 3. Now next step, create a parity matrix, because we want to create a generator matrix with the parity matrix. So that's why first we need to create a identity matrix, the k equal to 3, why k equal to 3, the here k is mentioned 3. So now you need to create a parity matrix. So now create a k cross n minus k. N minus k means the 5 minus 3 is equal to 2. So the n minus k matrix to represent the parity bits. So 2 is the parity bit out of code word. For n minus k equal to 5 minus 3 equal to 2. So let's randomly assign parity matrix values as per coding scheme design. Okay. So now here you can see, just for now you need to, so in this matrix are chosen based on this parity matrix. We have two parity bits. We have two parity bits. Two parity bits means two column actually denoted the two parity bits. Okay, 101 011, and before this 3 cross 3, that means the identity matrix. Okay, so now in this matrix are chosen based on how we want to calculate parity bits from the message bits. So now we have to understand what is parity matrix. Before creating our own parity matrix, we have to see some rules to create this parity matrix. In linear block coding, the generator matrix is typically formed by combining an identity matrix with a parity matrix. You can see the calculation also, the equations like G equal to I of K. K means the data bits or the message bits we can say, and the P is the parity bits, and I is the identity matrix of size K cross K, and P equal to parity matrix of size K cross N minus K. So that K and the before K both are same. So the parity matrix P decides how redundancy bits are added to the message bit. So to choose or design P matrix for encoding, need to follow some simple rule. The three rules are I have written over here. So now when designing the parity matrix, we need to follow some important rules. First, ensure it provides good error detection and correction capability, meaning the pattern of ones and zeros should be chosen so that the system can reliably detect and correct the intended types of errors. Second, the rows of the matrix must linearly independent, meaning no row should be a modulo to sum of other row. This ensures that each message bit contributes uniquely to the code word. And third point says, when you eventually form the parity check matrix H, its columns must be unique and non-zero. That means when you are creating a parity check matrix, its column must be unique and non-zero. Unique means it will not be same with the another row, another column. So no two columns should be the same, and no column should be entirely zero. So you can see over here the two columns are different. Okay. And no column should be all zero. This structure ensures that every possible error pattern affects the code word in a distinct and detectable way. So now let's continue the step 3. So using the parity matrix, so let's say we have 7 comma 4 linear block code. So k equal to 4, here you can see the k equal to 4 message bits, which is message bit, or we can say the data vector bits, which is also equal to the row of the generator matrix. Now, so rows, that means the 4 rows you have to write down, and n equal to 7 total code word bits. Out of 7 total, 4 and 4 bits are the message bit, and 7 minus 4 is equal to 3 bits for the data bits, sorry, parity bits. So n minus k equal to 3 bits for parity bits. Now P would be a 4 cross 3 matrix. 4 cross 3 matrix. Basically the P would be 4 cross 3. Why 4 cross 3? K cross n minus k. K cross n minus k. That was the rule for the creating a parity matrix. So you can see over here the identity matrix of size k cross k and parity matrix of size k cross n minus k. So now the k cross 3 will be the parity matrix row and column size. So now P equal to 1 0 1 1 1 1 0 1 and 3 columns over there. Okay, so you can see also the 3 columns are not the same thing. Okay, so 1 1 0 1 0 1 1 1 1 0 1 and 0 1 1 1. So these three are different each other, and also these three, as per the rule, the no column should be all zero. Every columns have a every columns have must have one ones. Now then the general matrix would be G equal to I of 4. 4 means the 1 0 0 0 1 1 0 1 0. That means the 4 column 4 row. See, 4 column 4 row. Over here you can see that 4 column, a 4 column 1 2 3 4. This 4 column for the data bits or the message bits, and then this and these 4 rows and these 4 rows. Okay, that means this 4 cross 4 is creating an identity matrix, and this 3 cross 4 is creating a parity bits. So these two things will be just side by side, we have to write down. Then you can easily create the generator matrix. Now the concatenate the identity matrix and parity matrix side by side. Okay, which means the like this. Okay, just this is another example: 1 0 0 0 1 0 0 0 1. This is the generator matrix. 3 cross 3 identity matrix, and after then the 3 cross 3, that means 3, and then 2 is the parity matrix. Then what will be the code word? So the code word will be the generator matrix, that means the identity matrix is 3, the length of identity matrix is 3, and the parity matrix is 2. So 3 plus 2 is equal to 5. So that means 5 is the code word. Simplified. So 1 0 0 0 1 0 0 0 1 is the general matrix, sorry, data bits, and 1 0 0 1 1 1 is the parity matrix. Now steps to create general matrix is the last stage. Okay, how to encode a message, represent a message bits as a row vector. So there have a row vector means that there have only one row, and 101, this is the message, and multiply. So message means whenever computer will understand any data or any input from any input devices, then it will convert to the machine language, which is called binary language. So that means it will create a packet wise messages. Okay, the block of codes it will create. So next, these are the messages will be transferred through wireless or the word. So multiply message vectors with G using modulo 2 arithmetic. So this is the main thing, the multiply message vector with G using modulo 2 arithmetic, that we can also understand. So first you just see the code word, which is C equal to M cross G. So now the 101, this is the matrix, and the before this is the generator matrix, and this generator matrix, if you want to, and one more thing, I hope this will not be clear. This in step 3 you can see the generator matrix is very long, like 7 columns are there. Okay, but the step 4 there have 5 columns. So these both the general matrix are because of the two linear block code. This general matrix created because of the 5 comma 5 comma 3, but this general matrix created because of the linear block code of 4 comma, sorry, 7 comma 3 7 comma 4. Okay, the both the general matrix have 7 comma 4, and the next one is the 5 comma 5 comma. Why 5? Because the 5 columns are the code word. There are 5 columns total, so that 5 columns are denoted the code word, defining the code word. But out of these 5 word, the 4 is the 3 is the identity matrix, 3 is the identity matrix which is called the message bits, and not message bit, the length of the message bit, length of the length only we can say. And this identity matrix, with this identity matrix we want to add a 2 more column, which will be calculated. 3 plus 2 is equal to 5. So 5 is the total general matrix. Okay, so sorry, 5 is the total code word, and 3 is the message bit. Okay, 3 5 comma 3 will be the linear block code for this example, and this one will be the 7 comma 4. So now we have to understand over here the multiply message in with general matrix. So before general matrix I have used the C equal to 101 cross cross means the multiply with the 1 0 0 1 0, this one, this 5 columns general matrix, multiply corresponding elements and add mod 2. So you have to add mod 2. Why mod 2? Then let's assume c equal to, now here you can see, now the multiply corresponding elements and add mod 2. So where we have to add mod 2? So because basically here you can see that 1 multiply with that 1 plus 0 into 0 plus 1 into 0 is equal to 1. Next, that 1 is written, 1 into 0 plus 0 into 1 0, and 1 into 0 is equal to totally 0. That means 0 is written. Next, 1 into 0 plus 0 into 0 plus 1 into 1. That means 1 is also written. Okay. Now next, the 1 into 1 plus 0 into 0 plus 1 into 1. That means 1 plus 1 2. So now we have to add, means we have to use the modulo to find out the actual digits. So 1 plus 1 modulo 2 is equal to 0 because the remainder will be 0. So 2 divided by 2 is equal to 2 divided by 2, the remainder 2 not divided, 2 modulo 2 is equal to 0. So the 0 will be there. So you can see at the last there have the 1 0 1, then 0 is there. Okay. After then 1 into 2 1 into 0 plus 0 into 1 plus 1 into 1. So basically 1 is there and both are 0. Okay. So both are 0 means the 0 plus 1. So 0 plus 1 equal to 1. If I will calculate with the mod 2, then obviously it will create a 1 because the remainder will be 1 only. So with the modulo 2, so that's why one time I had been used, and this is the 2 times you can see. This is the code word to transmit. Okay. So now in the next slide we can see that how the message actually we are transmitting. So now the fully encoding process. So let's understand how the full encoding process works in linear block coding. We start with a message or data vector D, or data vector we can say the message M. This is the original information we want to send. The length of the data vector is K, which is, this is the information bits, that is my message bits, and we want to send, which is the number of message bits. Okay. And K is the length of the bits, K is the length of the bits, that is the number of message bits. Next we create a generator matrix which is combination of identity matrix of size K cross K. We already have seen that K cross K on the left side, so that is the identity matrix, and parity matrix of size K cross n minus K on the right side. Okay. So here you can see the parity bits n minus K. Okay. K cross n minus K is totally parity bits. Okay. Thus this matrix is carefully designed so that it adds redundancy bits to our message for error detection and error correction. Once we have the data vector and the generator matrix, the encoding is done by multiplying the data vector with the data vector of the message bit. Okay. The linear combination message bit, we need to multiply with the generator matrix using the modulo 2 arithmetic. Then the result of this multiplication is called a code word, which is encrypted after encoding, and it has a length of n which includes both the original message bits and newly added parity bits. So next we have a numerical with us. Now numerical of linear block code, you can see that one example. Let's say you want to send the message 1011. So your data vector is data vector means the message bits 1011. You can choose any combination of 4 bits of your message like 0000, 1011, 1101, but here we are using 1011. There is no restriction, it purely your message content. Okay. So how is it encoded? We multiply this data vector by generating matrix, generator matrix, to create a code word. So here we already have used a generator matrix which is calculated with the help of the parity matrix. Okay. So you can see that 10000, this is the 4 data bits, 4 columns, 1000, 0100, 01010, sorry, 0001. So this 4 cross 4 is the identity matrix, and the remaining 1 this is the 3 the 2 4 cross 3, 4 cross 3 is the parity bits. Okay, 4 cross 3, why? Because the 1 1 0 1, this is the one column, this is second column, and this is the third column. This 3 column defining the parity bits, and these before 4 column defining the identity matrix of the gender matrix. Okay, so now multiplying these gender matrix with the message bit, okay, this data vector. So now here you can see the C equal to D cross G and 1011. The next slide you can see that 1011. So first, the first bit which will be created 1, then second bit 0, then 1, still it will placed as it is if 1 or 0 is there. If more than 1 is there, that means then modulo 2 we have to use. So 1 0 0 1 is if added, that means the 2 is created and 2 modulo 2 is equal to 0. Then 1 plus 1 plus 1, that means 3, the 3 modulo 2 is equal to 1. So now the 1 plus 1 2 is equal to, then the 0 will be there. Okay, so final code word is 1 0 1 0 1 0 1 0. So 1 0 1 1 0 1 0, 1 0 1 1 0 1 0. So this is our code word, and this way we can easily encode our data. So data means the message bit. Okay, and now it's clear. I hope it's clear everything about that topic, the linear block code, how we can encode the data. So next video we will understand about the Hamming code, and before next video we also can see some numerical or the other questions answers which can come in our exam. So if you like this video, then please like, share and subscribe my channel to see more interactive videos like this.